in this example, we're going to start by graphing our function first, and then we're going to use that graph to evaluate some limits here. So here I have the function f of x equals absolute value of x divided by x. This is a pretty tricky function to work with here. So we're going to take our time. We're just going to take some x values, plug them into our function, and try and find our y values. So I'm going to pick some x values. I like to work around 0, so maybe -2, -1, 0, 1, and 2. And I think that'll give us a pretty good idea of what's going on with our graph. So I'm going to take each of these x values and plug them into our function. So f of -2 is equal to absolute value of -2 divided by -2. Remember, absolute value will always give you back either a positive number or 0. So if you plug in a negative number, it's going to give you back the positive version of that number. So the absolute value of -2 would be +2 divided by -2. And if I divide those two, I have -1. So that tells me that I have a point -2, -1 on the graph of my function. So I'm just going to go ahead and plot that point for right now. -2, -1. I've got this point right here. And I'm just going to repeat this process a few more times with these other x values that we've chosen here. So how about -1 next? F of -1 is absolute value of -1 divided by -1. Again, absolute value of a negative number, that's going to give me back, in this case, a +1 over -1. And then dividing those two gives me -1 once again. So this time I have an x value of -1 and a y value of -1. I've got a point right here. Next we'll take 0. So f of 0 is absolute value of 0 divided by 0. Absolute value of 0 is just simply 0 divided by 0. But hopefully you caught on to this already, but if not, dividing by 0, remember, is just one of those things you're not allowed to do in math. 0 divided by 0 is something which we say is undefined or does not exist. So I'm going to say it is undefined. And that's going to be a little bit trickier to graph. We'll come back to that one once we have a better idea of what our graph looks like. So let's take our last two x values and plug those into our function. So how about f of 1 is absolute value of 1 divided by 1. Here, absolute value of +1. In this case, it's not going to change the sign. Remember, absolute value always gives you back either a positive number or 0. So absolute value of 1 is 1 divided by 1, which is also 1. So I have a point on my graph at 1, 1. I'm going to go ahead and plot that right now. Lastly, x equals 2. We'll plug that into our function. F of 2 is absolute value of 2 divided by 2. Absolute value of 2 is still +2 divided by 2, which is 1. So I have a point at 2, +1. So that means I have this point right here on my graph. And we could take a few more x values and plug those in if we felt like we needed them, but hopefully we're starting to see we've got a horizontal line right here on the left-hand side there at -1, and a horizontal line right there on the right-hand side at +1. Now the behavior at 0, we said that was undefined. It's a little bit trickier to work with here. Since it's undefined, I'm not going to be using any closed circles or anything like that. In fact, I need to use two open circles, one up here at 0, 1, and then 1 down here at 0 comma negative 1 to make sure that I'm telling whoever's looking at the graph that, hey, the function does not exist at 0. We have these open circles. Those represent holes. So our function does not exist at that point. So here is the graph of our function. So we have the graph of our function. Let's use this graph now to evaluate some limits, just like we've been looking at so far. So in part A, I want to find the limit as x approaches negative 1 of our function that we've graphed here, f of x. So here our x value of negative 1. Remember, I need to check both the left and the right hand side. So for the left hand side, move a little bit to the left. As I trace my way back towards x equals negative 1, I'm pointing at, looks like a y value of negative 1. But remember, I need to check the right-hand side too. So we'll move a little bit to the right. And as I trace my way back towards x equals negative 1, the two arrows are pointing at that same blue dot that I plotted earlier. That has a y value of negative 1. So my limit must be negative 1. Next, we'll move over to the right-hand side of our graph and we'll look at 2. So here at x equals 2, again, checking the left and the right-hand side. Start with the left-hand side. Okay, we're pointing at that blue dot right there at 2 comma 1. Move a little bit to the right. We're pointing at that same point, that same y value right there of 1. So that means our limit must be 1. So okay, those two, not terribly exciting. We've seen a lot of examples like that so far. What is pretty exciting is what's going on at 0, because that's where, right, that's where we had that hole. That's where our function was undefined. So let's look at it. If I say x equals 0, I'm just talking about right here. If I move a little bit to the left, trace my way back towards x equals 0, I'm pointing at that open circle right there. It looks like I'm pointing at that open circle at negative 1. But I need to check the right-hand side as well. So we'll move a little bit to the right, find our function. As we move back towards x equals 0, here this arrow, this side of my function, is leading up to a different y value. It's leading up to a y value of 1. So the left and the right-hand sides, they're pointing at two different y values. In this case, we said that the limit does not exist or is undefined. So I'll say that this limit does not exist. But I'd like to be able to say a little bit more about the behavior at 0. So we're going to introduce some new definitions here. We're going to introduce this idea of one-sided limits. So we're going to talk about a left-hand limit and a right-hand limit. A left-hand limit looks like this piece right here. It says, we write limit as x approaches c from the left-hand side. That little minus sign after the c is what tells us that this is a left-hand limit. So the limit as x approaches c from the left-hand side of f of x is equal to L if f of x gets close to L as x gets close to c from the left-hand side. Right-hand limit defined very similarly, but here in this case, rather than a little minus sign, I'm going to have a little plus sign to denote that this is a right-hand limit. So we write limit as x approaches c from the right-hand side of f of x equals L if f of x gets close to L as x gets close to c from the right-hand side. So I want to use these two new definitions. I want to evaluate the left and the right-hand limit at 0. So let's go back and look at our function here. Let me clean this up just a little bit. Let me erase that. So let's look at, how about for part D, let's start with the left-hand limit. And let me change my color up here. Let's look at the limits as x approaches 0 from the left-hand side of our function f of x. So here we're looking at 0. That minus sign tells me that we're looking at a left-hand limit. So I'm going to be looking at the left-hand side of 0. I'm looking at this piece of my graph right here. So again, you can kind of move a little bit to the left if you want. Trace your function back towards x equals 0, and what y value are we getting closer and closer to? Well, we're getting closer and closer to a y value of -1. So the left-hand limit in this case is -1. We'll add one more part right here, part E. Let's look at the right-hand limit now. The limit as x approaches 0 from the right-hand side of f of x is equal to, and let's go find that limit. So again, we're talking about 0 once again. That's kind of my starting point. We're talking about the right-hand limit. So in this case, we're talking about the right-hand side of my function. So I'll move a little bit over to the right, find my function. If I trace my way back towards x equals 0, what y value are we getting closer and closer to? Well, we're getting closer and closer to a y value of +1. So here in this case, the left-hand limit was -1. The right-hand limit was +1. We ended up with two different limits for both the left and the right-hand side. And what this means for me is if I look at this, if I know the left-hand limit is different than the right-hand limit, then the two-sided limit, which is what this guy is, the two-sided limit does not exist. And that's the last thing I'm going to leave this video with here. I'll leave it with a little theorem, which is like a little math fact here. It says the limit as x approaches c, and actually here, you know what? Let's just write this in plain English. I think that's going to be easier to understand. I'm going to say the two-sided limit which is limit as x approaches c of f of x, only exists if the left and right-hand limits are equal. Equal. So only if those two left and right-hand limits are equal will the two-sided limit exist. So if I wanted to go backwards, let's say I didn't know this limit did not exist. Maybe I didn't even have the picture. All I knew was that the left-hand limit was -1. The right-hand limit was 1. I can look at those two. I can say the left-hand limit, that's different from the right-hand limit. So that means that the two-sided limit does not exist. So that is a kind of a math theorem, a math fun fact, if you will. We're going to talk more and get some more practice evaluating one-sided limits in the next example.